Good morning, students. In yesterday's lecture, we have discussed on the characteristics of analog filter design, and also we have derived an equation for order of the filter for the given specification, and also we have solved some of the examples on the filter design. So let us continue with the yesterday's example. So let me share my screen. So yesterday we have started with this example. So design an analog Butterworth filter that has a -2 dB passband attenuation at frequency 20 radian per second and at least -10 dB stop band attenuation at 30 radian per second. And we have discussed on the steps of designing an analog Butterworth filter. So first we need to find the order of the filter for the given specification. Second, we need to round off it to the next higher integer. And third step is to find transfer function h of s for omega c equals to 1 radian per second for the value of n. And fourth one, calculate the value of cutoff frequency, that is omega c. And last, we need to find the transfer function h of s for the above value. So let us calculate first order of the equation. Let us calculate order. So the solution for this solution. So here first we will note down the given specifications. The given specifications are alpha p is equals to 2 dB at omega p is equals to 20 radian per second. 20 radian per second. And second one is alpha s is equals to 10 dB at omega s is equals to 30 radian per second. 30 radian per second. So these are the given specification. Let us, according to the first step, to find order of the equation. To find order of the equation. Order of the filter, we can call it. It's not equation. To find order of the filter for the given specification. So we know the formula of order of the filter, that is n greater than or equals to log of root 10 to the power 0.1 alpha s 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1 divided by log omega s by omega p. Here we know the values of all these specifications. So let us substitute those values and get the answer. So we will substitute these values, that is greater than or equals to, we'll have log of root alpha s value is 2. So it is alpha s we are having, it is 2. So we will get it is 2 into 0.1 is multiplied, or else simply we will write down all the values and we'll simplify that. 10 to the power 0.1 into 2 minus 1 divided by 10 to the power, sorry, alpha s is 10, it is not 2. So this is 10 and this is 0.1 into 2 minus 1 divided by log omega s is 30 by 20. 30 by 20. So if we simplify this further, we'll get the answer as 3.37. 3.37. So as we need to round off this equation, that is our step 2. Round off the equation the equation n to the next highest integer, the next highest integer, the next highest integer. So which we are writing it as n is equals to 4. So this is how we are calculating the order of the equation. Okay, so now let us move to the second part. Based on this specification or based on this order, now next third step we will follow. Third one is step 3. So what we need to do is we need to find the transfer function for the value of n. So step 4 it is. Step 4, what we are doing is the normalized low pass Butterworth filter for n equals to 4. The transfer function we can write it as the normalized low pass Butterworth filter, normalized low pass Butterworth filter, for n equals to 4 can be found. For n equals to 4, the h of s value, denominator value from the table as we can write h of s is equals to 1 divided by s square plus 0.7653 s plus 1 multiplied with s square plus 1.8977 s plus 1. So this is what we are written from table what we have discussed in the yesterday's lecture. From table for n equals to 4. N equals to 4 we have written that. And also we know that omega c is equals to omega p divided by 10 to the power 0.1 alpha p minus 1, 10 to the power 0.1 alpha p minus 1 whole to the power 1 by 2n. Or else this is equals to, we have it is omega s divided by 10 to the power 0.1 alpha s minus 1 whole to the power 1 by 2n. So that means here we have to decide whether we are calculating it for the omega cutoff frequency, we are calculating it for omega p value or omega s value. So it depends on, if it is low pass, we have to go for like omega p, and if it is again high pass, we have to go for this omega s. So then Let us calculate the value of this omega c based on the above equation. Let us calculate the value of omega c for the above equation. Omega c for the above equation. So we can find the value here. Omega c is equals to omega c is equals to omega c equals to omega p. We are having it is 20 divided by 10 to the power 0.2 minus 1 and whole to the power 1 by 8. I just substituted the value of omega p, which is just 20. Then alpha p, we have it is alpha p is 2, and then n equals to 4. By substituting all these values, we'll get this. So this will be equals to, if you simplify this, we'll get the answer as 21 point. If you simplify this, we'll get the answer as 21.3868. So this is what we have calculated the cutoff frequency value. That is our step 4. And then the transfer function for omega c equals to, then we are writing a transfer function for omega c is equals to. So here we will write the transfer function. Transfer function for omega c is equals to 21.3868 can be obtained by substituting guess by the value guess by omega c in h of s. So this can be written as, so we will write this as, this can be written as, now h of s is equals to here s is replaced by s by omega c. So 1 divided by s divided by 21.38 square plus 0.765 into s divided by 21.38 plus 1. This whole thing is multiplied with another term. So I will write it separately so that we can understand it very easily. Okay, so let me take out this part and then we'll go for the further step. So that is, how to find h of s value. We are writing it is like, to find h of s value, we are writing h of s is equals to, that is transfer function of analog filter, 1 divided by s is replaced by s divided by the omega c value, that omega c is 2.21.38 square plus is again 0.765 multiplied with S divided by 21.38 plus 1. This is the first bracket term. And the second bracket term is S divided by 21.38 square plus 1.84 is divided by 21.38 plus 1. So further we need to simplify this, and this will be equals to, we'll get 0.2092 into 10 to the power 6 into 10 to the power 6 divided by we'll get the value as S square plus 16.36S plus 457.39 which is multiplied by S square plus 39.51 S plus 457.39. So this is the way how we are designing an analog filter for the given specification. So this is our final answer. Let's take one more example. For the given specification, example number again 3 it is. For the given specification, example 3. For the given specification, design an analog Butterworth filter. Design an analog Butterworth filter. Design an analog Butterworth filter. Okay, let us do the solution for this. Or first we'll note down the specification. It is given as like 0.9 less than or equals to mod h of j omega mod less than 1 for 0 less than or equals to omega less than or equals to 0.2 pi, then mod h of j omega is less than or equals to 0.2 for 0.4 pi less than or equals to omega less than or equals to pi. So this is the question. So for this we need to solve the example, or else we need to design an analog Butterworth filter. To design an analog Butterworth filter, solution for this. So from the given specification, we can write down the values. For the given equation, we can write omega p is equals to, it is 0.2 pi whereas omega s is equals to, we have it is 0.4 pi, 0.4 pi, and the value of this 1 divided by square root of 1 plus epsilon square will be equals to, it is 0.9, and 1 divided by square root of 1 plus lambda square, 1 plus lambda square is equals to, it is 0.2. So this, as per the diagram, we know that these specifications, we know that this, as per the diagram, we can write this structure, we can write it like this. Okay, so here, so this is what the graph we are having for the low pass filter. So here, so this is at the point we are just writing, this is at, and this way, if our response is coming, if we have a response this way, that is, it will be like this. This is the response of our low pass filter. Okay, so here at this point, this is the value of omega p, which is equals to 0.2 pi, and this is the value omega s, which is equals to 0.4 pi. This is omega s, which is equals to 0.4 pi. It is. We take this as a separate value. So यहाँ पे this is omega s, which is equals to 0.4 pi, and this is with respect to omega. And here, this is a magnitude h of j omega. And here, the value is, this is 1.0 as a value we are having. This value we are having as 1.0. So here it is 1.0, and this is 0.9, and this is 0.2. So likewise, with this specification, we can plot this magnitude response. This is what we are calling it as figure A, as a magnitude response. Figure A, which is magnitude response. Magnitude response, we can call it is. Now, once after knowing all these values, so we can calculate the order and also the other values. So this is how, with this specification, you can find out the values. We can find out the values of epsilon and lambda, and then further we can calculate the order, and we'll simplify that. Okay, so let me continue for this. Now, from the given specification, we have to get the value of, epsilon and lambda. So if you simplify that, we'll get it as epsilon is equals to, epsilon is equals to, as from the previous case, previous equation, we are just writing this 1 divided by square root of 1 plus epsilon square is equals to 0.9. If you simplify this, with this we are going to get the value of epsilon as epsilon is equals to, we'll get it as 0.484. Likewise, 1 divided by square root of 1 plus lambda square, which is equals to, we have it is 0.2, which is equals to, we'll get the value of lambda as, 4.898. Okay, get the value as 4.898. So we know the formula of calculating the order in terms of lambda and epsilon. So we'll use that here. So n greater than or equals to log of lambda by epsilon divided by log omega s by omega p. Log omega s by omega p. So this is equals to, we'll write log lambda value is 4.898 divided by epsilon is 4.484 whole divided by log 0.4 pi divided by 0.2 pi. 0.4 pi divided by 0.2 pi, or else this will be equals to, we are getting 3.34, or the next highest integer value is n is equals to 4. So your order of the filter is 4. From the table for n equals to 4, we know the value again. The same procedure we have to follow as we have done for the previous case. So with the same procedure, we will find the transfer function and the analog filter transfer function we will calculate. Okay, so then from the table for n equals to 4, we'll calculate from table for n equals to 4. We can write a transfer function value as h of s is equals to 1 divided by s square plus 0.765 s plus 1 multiplied with s square plus 1.84847 s plus 1. Now here again, we know that the omega p value, or we know that the omega c we can calculate. We know that omega c is equals to, we have formula omega p divided by 10 to the power 0.1 alpha p minus 1 whole to the power 1 by 2n, or this is equals to omega p divided by, this is like the value of epsilon whole to the power n. So this complete value we are writing it as epsilon and whole to the power n, or this will be equals to, we'll get the value as, by substituting the values of omega p, its omega p is again 0.2 pi divided by the value of this epsilon we are having is 0.484 to the power n. N we are having is, that is 1 by n. So 1 by 4, which is equals to, we'll get the value as 0.24 pi. 0.24 pi is the value of omega c for 5. That is omega c is equals to, we got the value as omega c is equals to 0.24 pi. Now We can calculate H of S by substituting H of S equals to H of S at S is replaced by S divided by 0.245. Okay, now let us simplify this final to calculate the analog transfer function. We'll simplify this. So after simplifying this, we will get the answer as, for simplifying this, we'll write H of S is equals to, that is the analog Butterworth filter. H of S is equals to, we can write it as 1 divided by S divided by 0.245 square plus 0.765 into S divided by 0.245 plus 1 multiplied with another bracket term is, again we'll do the same thing, S divided by 0.4 into 4 pi square plus 1.84 into S divided by 0.245 plus 1. So if you simplify this, after simplifying this, we will get the answer as 0.323 divided by 0.323 divided by, we'll write S square plus 0.577 S plus 0.057 pi square multiplied with another term S square plus 1.39 square plus 1.3993 S plus 0.076 pi square. So this is what the analog transfer function, what we have designed for the given specification. So this is the way how we are solving the equations for designing a filter for the different specifications. Okay, so then let us take one more example, last example we'll take on this part. So that is, I'm just trying to get the examples of different specifications so that we can solve very easily. So let us take the next question. Example number 4 it is. Question number 4 again. Question 4. Design an analog low pass filter. Design an analog low pass filter. Analog design an analog low pass filter. Analog low pass Butterworth filter. Low pass Butterworth filter. Butterworth filter. Pass band and stop band cutoff frequency are 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 800 radian per second, 800 radian per second and 1800 radian per second, 800 radian per second and 1800 radian per second. The passband attenuation is the passband attenuation is the passband attenuation passband attenuation is passband attenuation is minus 3 dB and stop band attenuation is and stop band attenuation is minus 10 dB. So this is the example. So for this, let us design an analog filter solution. The given specifications are omega p is equals to 800 radian per second, 800 radian per second, comma, omega s is equals to 1800 radian per second, 100 radian per second. Alpha p is equals to 3 dB and alpha s is equals to 10 dB. So the value of n will be equals to n, we are going to get it as order. We are calculating n equals to log of a divided by log of 1 by k, where we are getting this value as simply substituting all the values, we'll get 1.35, or which will be equals to, we are writing it as simply 2. So order we are getting it as 2, n equals to 2 it is. Then the transfer function for normalized low pass Butterworth filter, the transfer function for normalized low pass Butterworth filter, transfer function for normalized low pass Butterworth filter for n equals to 2 is Butterworth filter for n equals to 2. We are going to write it as the normalized filter for n equals to 2 is h of s is equals to 1 divided by s square plus root 2s plus 1. So once if you know this value, we can calculate further cutoff frequency and then the final analog transfer function. Then Let us calculate to calculate a cutoff frequency to find omega c. We have again it is omega c is equals to omega p divided by 10 to the power 0.1 alpha p minus 1 whole to the power 1 by 2n. This is equals to, we are getting the value as 800.96. Substituting all the values, we will get this. Or else simply we are writing omega c equals to 800 radian per second. 100 radian per second. So then we are calculating h of s. We are calculating h of s is equals to h of s by replacing s by the value s divided by 800. So we will write h of s is equals to transfer function. We are getting it as h a of s will be equals to 1 divided by s by 800 plus root 2 into s by 800 plus 1, or simply this is equals to 1 divided by, that is 64 lakh divided by s square plus s square plus s square plus 1131.37 s plus 64. Okay, so this is what the answer we are getting, transfer function for this particular example. So this is all about the varieties of examples on the filter designing part. And then at the end, we will discuss about the filter implementation techniques. At the end, we will discuss about the filter implementation techniques. That is IR filter implementation technique. So let me start with this. So here in this, already we have discussed on this part, the difference FIR filter implementation techniques. It's not FIR. We are writing it as, we need to write filter implementation technique for IR filter we have to write. So FIR filter implementation technique first we'll discuss, and then we'll discuss on the IR filter implementation technique. So here, as the FIR filter implementation technique, we know the difference equation for an FIR filter is given as y of n equals to k equals to 0 to n minus 1 h of k x of n minus k, where h of k will have the coefficients, that is filter coefficients, and for implementing this we need to choose a suitable structure, and then we need to analyze that the number of bits used to represent variables in carrying out the arithmetic operations is adequate. So that means, so we need to perform the proper analysis, the how many number of bits we require to perform the arithmetic operation. And here the final stage is to implement the filter. And the key issue here is essentially to produce software code or a hardware realization of the chosen filter structure. Then next, an examination or an example we are taking it as like y of n equals to k equals to 0 to n minus 1 h of k x of n minus k. Here y of n involves only multiplications, addition, subtraction, and delays. Okay, so that means it will show how this computation we are performing. So here, thus for the implementation, we need the following basic components. That is, we require a memory, that is RAM, to store the present and past inputs x of n and x of n minus k. Memory, we require a RAM or ROM for storing filter coefficient, that is h of k. A multiplier, that is hardware or software again, adder or ALU. So these components together with a means of controlling them, they constitute a signal or digital filter. So this is how the block diagram I am just showing here, how this implementation is performed. So here the input of the source is analog, then digital to analog converter is also required. The output is also analog, then an ADC is also required. Okay. Means because as we know that the source is analog, so we need to use a DAC, that is DAC, to convert it into the digital form. And at the output side again we require the output, so we need to convert the digital to analog form. The structure of real-time filter has the following. So already we have discussed this block. So input filter, ADC with sample and hold, then digital signal processing, DAC to convert digital to analog converter, and finally we have an output filter so that we will get the smooth response. So that is we are calling it is the already we have discussed the block diagram of this digital signal processing. So they're all these components we have discussed much more. So filter implementation is divided into the two parts, that is hardware part and the software part. This division is somewhat artificial in the modern DSP because there are almost no more truly hardware solutions, as most devices that use filter are programmable. So this is about the FIR filter implementation technique. So this completes your unit 6. Thank you.